Here is the list of the penetration tests. We are using man-in-the-middle attack to modify the control command value in the network side, authorized device, and the attached unauthorized device. In the man-in-the-middle attack case, the cloud sends the same control command as the normal case, but attacker uses EtherCAP to make the man-in-the-middle attack successful. As the result, the site data manager receives a modified control command value according to the attacker intention and delivers the modified command to the security module and solar inverter. As a result of man-in-the-middle attack, the site data manager, the security module, and the solar inverter receive a modified control command value 0. And it is the same value as the default value set. These results present the blockchain ledger status before and after the update transaction. The blockchain ledger's different parts are modified status. With the hash comparison in the blockchain ledger, we can detect the attack and attack location. In this attack scenario, we assume that one of the authorized devices has compromised by the attacker. In our experiment, we manipulated the site data manager's code. When an attacker has the device's permission, the attacker can make backdoor and send a malicious file, manipulate source code, and so on. In this penetration test, the attacker modifies the site data manager's source code so it acts like the man-in-the-middle attack, which filters the control command value and sends it to the site security module. Since the attacker has compromised the site data manager and manipulated the source code, the site data manager, the security module, and the inverter receives modified control command. The result in the blockchain ledger is the same as penetration test 1 attack case. All control commands communicated in the network will be reported to a blockchain ledger and update transactions comparing the control command's hash value. Finally, the site data manager status and the security module status are shown as modified. In the penetration 3 scenario, an unauthorized device is attached to the local network. So the attacker can forge the control command and send it to other OT devices, such as site data manager, the security module, and the inverter. In penetration test 3, although the cloud doesn't send a control command, the attacker forges the control command and sends it to the site data manager. This control command will arrive at the inverter, and all devices are updated the control command to the blockchain ledger. In the penetration test 3, because the cloud doesn't send the control command, there is no asset for cloud. In the blockchain ledger, there are only 2 assets for the site data manager and the security module.
Hi, this is Bohyun. PT4 is a case when the security module receives an unauthorized inverter. However, in the malicious case, a different hash was calculated then updated to the blockchain server. After comparing the calculated hash with the original hash in the legitimate club server, the blockchain ledger shows that the file in the security module has been modified. PT5 is a case when the security module receives malware. However, in the malicious case, it shows a different hash value because this hash has been registered or analyzed as malware in the cybersecurity vendors. Virus total shows 53. After the reverse code engineering, it shows that the original file type is either exe or DLL. Also, IP address is not included, but 23 of URLs are included in this file. And the escalate privilege behavior is included. Therefore, the final status is concluded as malicious in the security module. After the decision, the security module reported the result to the blockchain server to update the audit trail. PT6 is a case when the inverter directly receives a new firmware or an already installed firmware is modified through unknown access. When the firmware file is transferred from the USB flash drive to the firmware folder in operative Windows PC, the Python's watchdog module detects the file creation event in the shared folder of Raspberry Pi. After the detection, the hash of the firmware file is calculated, then sent to the blockchain server. Here, the current hash status in the security module is unchecked. After comparing the calculated hash with the original hash in the legitimate cloud server, the blockchain ledger shows that the file in the security module is modified. Please take notice of the box on this screen. A valid version of the firmware file has already been installed in the security module. If the valid version in the security module and the current version in the inverter are not matched, the security module will initiate a rollback process. In this video, the firmware in the inverter is rollback with the valid version due to the mismatch. And this result is sent to the blockchain server. The blockchain ledger shows that the file in the security module has been recovered.
In the experiment, there are a user and an inverter. The inverter is running with a firmware which default status is normal. This status can be changed to modified when an attack or malicious action is triggered. Based on the access control rule, no one can update the inverter information through the transaction. When the user tries to update the inverter's information, the access will be denied. After the admin has changed the status back to normal, the user can update the firmware information of F version 1.5 and a new hash value.